Hey guys, welcome back to Camilo's Notebooks and Mathematical Proofs and Ideas, where we rep our set, whichever your set is. And today we're going to be talking about a few of these sets, namely the complex numbers and the quaternions, and other variants of it like the split-quaternions. In our video today, we will demonstrate the useful representations that I use in mathematical physics of the complex numbers, quaternionic and split-quaternionic, and other signature division algebras over the real numbers. These are special representations that provide useful embeddings into matrix algebras, and there's also analogs for the higher dimensional cases. So let's consider the complex numbers, which again are just going to be the numbers of the form z equals, we could use a or b or x plus I, doesn't matter, x plus y I, where x and y are real numbers. Recall that this division algebra is in fact a field, and this field has these special properties. Its squared is equal to z bar equal x plus iy. We're going to identify it. So there's going to be an arrow going both ways. We're going to identify it to the matrix Z in the 2 by 2 real matrices. Of this, we're going to identify it to one, and the map is going to be given by little z maps to big Z, which is going to be the matrix x minus y. And obviously, why are we going to do this? Because of exactly this fact, that the norm of z squared, again, which is z bar, happens to be the determinant of capital Z. In other words, if we call this map tau, we have that the norm of Z equals the determinant of tau of Z. Consider a vector Z and Cn. So Z, I'm going to stop writing, I'm just going to keep writing Z, I'm going to stop writing the little arrow, is a complex vector, Z1 to Zn. Well, I'm going to map that, I'm going to call the map tau as well to tau of Z, defined to be this little tau of all the and there's shorthand for this. Each of these is a 2 by 2 matrix, so that's a complex matrix. This is a real matrix, a 2 by n real matrix. x1, negative y1, y1, all the way, where obviously zi is xi plus I, zj is xj plus yij. The norm of z squared is the norm of the components, so we could write this as the sum from j equals 1 to n of zj bar. The norm will be preserved under the embedding of tau, allowing for the algebra representation. So to summarize these embeddings or representations, so the whole point is you can see the complex numbers, or one by one, embedded inside the 2 by 2 real matrices. And also, and equivalently, we can see the n-dimensional complex numbers embedded in the matrices of 2n by 2n real matrices, which is of course isomorphic to the 4n real matrices, and which of course is isomorphic to r to the 4n. Embedding is given by the subalgebra of m of the 2 by 2 real matrices of this form, exactly x, negative y, and y, such that x and y are in R. Consider these matrices inside M2R. And that's basically a copy of the complex numbers inside. We can do a similar thing to the quaternions. Remember, a quaternion, we call the division algebra H, it's not a field, contains, we call the quaternions Q, and it's usually some, for example, where here H is identified with R4, of course, and is as the span, the real span of the basis elements 1, I, j, and k, with the relations, of course, that I squared equals j squared equals k squared equals minus 1. From here, it's equivalent that I times j, or you probably already know it's k, so we can factor out a j, and so we can express this a plus bi plus cj plus dk as a plus bi plus c plus di, all of it times j, which we'll call this the complex number z, and this the complex number w, times j, the basis vector. So this gives us this identification, but the complex version. We can identify the quaternions with c direct sums, the complex numbers, times this basis element j. From here, it's equivalent that I times j, or you probably already know it's k, so we can factor out a j, and so we can express this a plus bi plus cj plus dk as a plus bi plus c plus di, all of it times j, which we'll call this the complex number z, and this the complex number w, times j, the basis vector. So this gives us this identification, but the complex version. We can identify the quaternions with c direct sums, the complex numbers, times this basis element j. And of course extending to hn as well. The identification here is, of course, q will map to tau of q, which you can call capital Q if you wanted to, where once you have this identification, we can map tau of q to z bar, negative w bar, w. And again, we have the same thing. If you recall the norm squared of q is exactly a squared plus b squared plus c squared plus d squared. which is exactly going to be the determinant of tau of q, which is is a 2 by 2 matrix, z times z bar plus w bar. So of course this is a squared plus b squared plus all the way to d squared. And in exactly the same fashion, we use this to extend it to higher dimensions, namely to an n-dimensional quaternion, an Hn. Also, we're going to call it Q, but it's going to be a n-tuple of quaternions. We're going to map this to tau of Q, where tau of Q is going to through tau to tau of q is going to be given by the matrix given by tau sub q sub j equals 1 to n. In other words, of course, tau sub q1 all the way to tau sub qn. The embeddings, specifically tau sub s, was crucial in helping me develop a theory of split-quaternionic functions, where I'm just considering functions from hn s to h or to hn. Maps or functions, either one. You could just call it hs1. But the split quaternions are pretty hard to work with, so it was way easier to work with these 2 by 2, 2n by 2n real matrices, complex matrices. So hopefully you got a flavor. If you have any questions, just ask me down in the comments. I think this is pretty basic. Hopefully I didn't explain it too fast. Not too sure that I didn't. Hopefully again you'd enjoyed. Look for me on Instagram at Camilo's Notebooks. I was supposed to have that written here, but obviously I don't because I'm lazy with the editing. Again, thanks for tuning in, guys. I'll see you in the next one.